So let's wait for over 2 3 minutes, and by the time I'll share the slide. So like the previous week also. So first of all, good evening everyone. So we meet here for the week 2 discussion, and I hope yesterday also you had one TA class, TA taking us the doubt clearing session class. And so what we will do today is we'll have some brief overview, and then we have the numericals, and we can discuss those numericals. And this week, sir has mainly taught about the transmission line modeling, and mostly it was concentrated. The discussion was mostly, or the lecture was mostly concentrated, means focused on the long transmission line. And so we'll also do a bit of that discussion, and then directly, as sir as the mathematical derivations that sir has discussed is well detailed. And so what we can do is that we can wait 1 minute or more, and then let others join. Are the previous weeks notes and all these things accessible from your end? Okay, okay, thank you. Thank you. And the video recordings too, right? Okay, nice. So, okay then, let's begin. And as previously told that, as I've told that previously that today's this week's for work, the lecture series was mostly designed on the discussion of the transmission line. And will as the days will move forward, we'll see that how the reactive power compensation and all the importance of power electronics applications in power systems will be detailed. But for the time being, a bit of power system applications or power system modeling, designing, and all these things will be discussed. So you will find this course tilting towards power electronics from week 4, I guess, mostly. And so, as we all know that the importance of transmission line. So, as anyone can volunteer, what's the importance of using these transmission line? We could have generated it in the locality, and then they distributed the power to the users or the customers. can be of any type, industrial, commercial, residential, but the transmission lines comes into picture. So what's the need based on the geographical aspect and all these things? What's the importance?
So these thermal plants, they emit a lot of pollution, and
Yes,
cities and all, like, it is tend to keep it far away,
yes,
towards the inside, so that like pollution does not happen in the city. So that's why it is somewhat in the interior areas, and we have long transmission lines to transmit the energy from the power plants to our
yes,
discom
yes. To the load centers, yes.
center. Yeah.
So that's correct. That's correct. So mostly the transmission lines, so the importance of transmission lines comes into picture the as in the present context, the thermal plants mostly, as we have discussed in the last day also, that mostly the power is still till date the power generation is mostly participation mix of the thermal plants is still the highest, and accordingly, since the power plants are located far away from the load centers, we need to means take that power from the generating plants to the customer end. So the power evacuation that is being helped by these transmission lines. So the major limitation in the modern day transmission line is that the right of way. So the right of way, to get the right of way, it has become a major challenge, and that's the need of various kinds of what people would nowadays see, that the width of the transmission lines, because these transmission lines would go over some means farmlands and all these things, so hilly areas. So people own those places, right? So mostly the farmlands, the villages, the towns everywhere, the localities over which these transmission lines would be constructed, those areas are owned by people. So to get the right of way for these transmission lines, and another thing is that the cross arms, the transmission line cross arms, people are trying to increase the or work on the dielectrics part, so that huge amount of voltage levels that can be transmitted, if we means more the distance of these cross arms, the more right of way is required. So nowadays power grid is also working on various aspects where these cross arms are targeted to get reduced, whereas the dielectric properties of these two materials, on the people are working on the material aspect, and to improve the dielectric strength of these materials, the transmission, so that the right of way can be reduced, because attaining the right of way has become a major issue. The solar plants means the in the Rajasthan project means the Rajasthan RE renewable energy project. So power grid is facing major challenge, because there is amount of surplus amount of generation means power that is being generated by the solar. The energy needs to be delivered somewhere. So there are some times where the transmission line is fully loaded, so there is no option to add more power to those lines. So in those cases, people must be aware. Means those who are working in industries, they are also aware that they can't do so. In those cases, these power plants needs to be operated off MPPT. So that's a drawback. So people are still working on transmission line setup planning problems. So in those cases, uh, the aspect of the load flow analysis and all these things becomes a major takes a major role. Optimal power flow. So with this, the transmission line that majorly we see is typically subdivided or classified into three segments, which is small, medium, and long. So accordingly, short transmission line, or we may say the smaller transmission line, is based on the length less than 80 kilometers, and the medium is from 80 to 250 or 240, and more than 240 to 50 kilometers we consider those as long transmission lines. The assumption is in the shorter transmission line is that systems and all equipments, all the components, line parameters are considered to be lumped, and the capacitance, effect of capacitance is eliminated, because the lines being shorter. So in those cases, the effect of capacitance is eliminated. In the medium transmission lines, the capacitances are considered, but these are also lumped according to the there are pi models, T models, and all these things. And on the other side, on the long transmission line, the capacitance effect and all these things are also considered, and it operates in the distributed fashion, means distributed consideration, or you may say uh, distributed parameters are considered, where each line, as we have already seen, Sarah's detail, and the mathematical derivations have also been discussed pretty well. So, if you have any doubts, you may ask. Otherwise, we will. Another thing is that so many of you might have heard the term Ferranti effect, right? Anybody aware of the term Ferranti effect? So,
Yeah, yes, sir.
so can you please detail if you
Like
already?
sending end voltage is greater than the, for example, receiving end voltage is greater than the sending end voltage. That is called as Ferranti effect.
Yes, yes. And under what circumstances this this phenomena occurs? Any idea? Otherwise, we'll discuss.
During no load situations, or when a lot of energy is stored in the capacitive elements in the
Yes.
transmission design.
Yes, in the no load situations or very lightly loaded conditions, in those situations, these conditions, the Ferranti effect is observed, where the receiving end side voltage becomes higher than the sending end side, and this is the major aspect in the which is generally observed in long transmission lines, right? So, considering the Ferranti effect, it is mainly, as we have discussed, in the no load condition, or very lightly loaded condition, and the VR becomes greater than VS, means sending end is lesser than receiving end. So in the option, or this phenomena is generally observed when the capacitive effect is more. So is more. And the other thing is that when we as you are also aware with what about the ABCD parameters, right? That Sir has discussed. So ABCD parameters, if one is aware.
Yes.
So you can see, just I'm writing down the for lossless transmission line, as far as detailed for lossless transmission line. What is the this is the receiving end side voltage, right? Let's say VR. Okay, from the sending end VR. Okay, let's write from the uh, considering the receiving end side as the reference, VR plus the IR, right? So now the system is lightly loaded or no load. So in these cases, what will be IR?
Zero or close to zero.
Okay, so 0 or tends to 0, right? So there would be no effect of this, so we may neglect this part. So this can be rewritten as AVR. Okay, so VS can be written as AVR. Now VR is equal to VS by A, and we know that for lossless transmission line, for this is an assumption to avoid various mathematical complexities, and getting tends to similar results. So it's not nothing like that. Yes. So for lossless transmission line, so we know that A is cos gamma L. So what is gamma again? Gamma is
root over
alpha
by z.
plus J beta, right? But when it is lossless, so the effect of alpha is 0, right? So gamma becomes J beta, means for lossless condition, I'm saying. So if we just place A, so now A becomes cos beta L. So this is A, and what we have, let's say this is equation 1 and this is equation 2. So if we place this one here, so VR becomes, so so substituting 2 in 1, so we get VR is equal to Vs by cos beta L. So so in any case, considering the transmission line to be a long transmission line, so maximum value of cos beta L will be 1.
Yes.
If the value reduces somehow, if the value cos beta L will reduce to 0 max, at max it may reduce to, means the minimum value would be 0. So let's not consider 0 here. So in any value which is getting a bit slightly deviated from 1 would result in VR which will be greater than Vs,
Yes.
right? So uh, so so we may say when cos beta L is less than 1, in those, any of those cases VR will be greater than Vs. So this effect is called Ferranti effect, and this is seen in the lightly loaded condition. So we can do one thing. So as we have discussed this Ferranti effect, the effect of this Ferranti effect, so we can verify this with a numerical. So I have a numerical problem. Okay. So you also please participate so that we can. So you will get to means you will find that how this line length is impacting the VR value, means how the voltage level gets upgraded. So this would be validation of this mathematical derivation. Okay. So so this is a small numerical. I guess this one is okay with everyone, right? This discussion.
Yes.
Okay. So let's validate with a numerical problem. So I have the data. So the data is uh, okay. So the data is for a 400 kV. Sorry, not 400 kV. 400 kilometer open circuited line, transmission line, or let me write open circuited. Otherwise, open circuit transmission line with parameters L is equal to 1.2 millihenry per kilometer, and C is equal to 0.01 microfarad per kilometer. The sending end voltage Vs, that is Vs is, let's say, 220 kV. So in this case, find Vr. So these are the values given. So please find Vr. So to find out Vr, what is required with the given values of L and C for lossless transmission line, what we can calculate?
ZC and beta.
ZC. So ZC is the, what is it called? ZC. What is the term also known for ZC? Characteristic impedance, right? Or surge impedance.
Yes, surge impedance.
So from there, so please calculate. L is given 1.2 into 10 to the power minus 3, and C is given 0.01 into 10 to the power minus 6. Square root of 6. So C, so 6 cancel. Okay, let's do one thing. 3 and 3, this becomes 3 and 2. So 10 to the power minus 5 and 12 into 10 to the power minus 6. So square root of 12 into, okay, 346.41, right? Okay, thank you. 346.41. What will be the unit? Ohm. Right? So once we get this, now what we'll have to find? The value of
Beta.
beta. Yes. So how to get the value of beta? Beta is j beta. So we may say j beta. So j, or we can directly find beta. So beta we can do as root under LC and multiplied by omega, right? Omega. And frequency, consider the frequency, you will have to consider the frequency as 50. So frequency as, so frequency 50 hertz. So again, if anyone would volunteer, that would be a great help for the value of this one. So it will be 2 into 5 into 50, and okay, thank you. So let me write it LC here and directly write the value. I hope everyone is understanding, right? What is the value? 1.088 into 10 to the power minus 3. So you'll have to find it, this one in radian, right? 1.088 into, is the unit, so in rad per kilometer, what will be the unit, what will be the value? Radians per kilometer.
Radians only, right?
Hmm. Is the same value coming? Okay, let's continue then. Final answer, if I have the final answer, we'll match it. So what will be VR? So VR will be VS, sorry, this will be VR, VS by A, right? So VS by A, and um, let's do one thing. So A, as we have seen, A is cos L, so cos beta L. So length of the line is given as 400 kilometers. So cos of uh, beta L, beta means 1.088 into 10 to the power minus 3 and multiplied with 400. Something is wrong at this. Cos beta L value of A is coming as, just have to calculate. So scientific mm, radian mm,
Sir, I think we need to convert this beta value into radians. I mean degrees
yes,
in
yes.
180 by pi, so that we will get 24.93 something.
Yes, some there is a issue with these values because, okay, just let me, I'm calculating it here in the screen, so in the recordings you will get to see. But, so is this value of beta correct? Because root under LC, root under LC is L and C values 1.2 into 10 to the power. So 1.2. So I am sharing the screen so that you all can see this one. Calculation is this. Yes. So the value is L is 1.2. 1.2 into C is 0.01 into 10 to the power minus 9, I guess, for micro and milli. So minus 9 10 to the power minus 9. So if I do square root of this, square root of this one, and multiply with
314.
314 0 yes, it's coming to the same value, right? Okay. So it is coming to the same value, right? This one is fine, yes. And sorry. Okay, let me then share this one. Hmm. So this one is correct. So if we put the value of so value of A is cos beta L, right? So cos beta is 0.001088 into 400. So
Sir, into 180 by pi.
into 180. Oh, acha. This one is radian, right?
Yes.
Okay. So in that case also the value won't be uh,
By pi, sir.
by pi. Sorry. 180 by pi. So in this case also, what will be the value of cost?
Degree is 24.92 and cost value is
0.96.
0.96.
906.
Cost of 24. Okay, let me see.
906, sorry.
0.906. Right.
that's right. Yes.
Okay. Thank you. So in this case, what we can observe is that so VR will be more. So what is VS? VS is given 220. So 220 by 0.91. If I write approximately 0.91. So the value will be 220 by 0.91. So 241, right? 241.76 kV. So the receiving end voltage is getting impacted, right? So please do one thing, just put this 400 instead of 400, please try with the value of 600. So you will get to see that this value will reduce further. So this value will reduce further. So if these 400 is replaced with let's say 600, let's take on the higher side. So you will get to see that this value will be impacted. So if you can do, so you can see that this value will be lower than this 0.91. So in that case, the VR will also, the VR value will increase, right? So what we get to see is that more the length of the line and in the no load condition, the receiving end voltage will get impacted due to this Ferranti effect, right? I hope this is clear.
Yes, clear, sir.
Okay. Okay, this was my main aim of showing the impact of the length of, so got some issue with the calculation here. So thank you for your help. So that's it, and so there are a few more questions again. So this is a common question, common data. So what you can do is that you can take a screenshot or anything, because uh, 7 questions would be depending upon the same values. We'll use the same value for question 1 to 7. So you may take some time, you may write it somewhere or take a screenshot, and we'll do the 7 numericals one by one. So it's as per your wish. I can wait 1 or 2 minutes. So the way that you will feel comfortable, please let me know. So once you are done, please let me know. I'll wait for 1 2 minutes so that you go through the question. In this question would be more or less similar to the one of the questions given in this assignment. So the values are different. So these are the previous year questions. So you will get to see or at least have some flavor of how the assignment questions would look like, and it will be easy for you to solve this one also if we discuss. This kind of questions are same, values will be different. So more or less same, not exactly, but more or less we will get to see similar type question in the assignment. So is it okay? So can we start with the questions? Okay. So for everyone, can I please respond some like or anything if I give, so that I can understand that everyone is fine and we may proceed with the questions one by one. Okay, okay, thank you, thank you. So time and again I'll come to this slide. Okay, so no issue. So for the first question, question number 1. So question number 1 is, determine the load impedance which transmission throughout its length. So phase constant we also need to determine. So this is the question. Determine the load impedance of a given phase for which the transmission line voltage remains the same throughout its length. Also determine the phase constant beta. I hope the question the data you have taken. So I'll keep the question in the front page. So let me do something. Let me give the options. Since the options are also there. So by the time you try to solve, and I'm writing down the options. So, so these are the options. Determine the load impedance. So transmission line voltage remains same throughout. Yes, D is the correct answer. Yes. So remains same when? If the line impedance is equal to the which impedance?
ZC, surge impedance.
Yes, characteristic impedance. Yes. So surge impedance. So that's the. So if we equate the same, means if we need to just calculate the value of ZC. So this is the first part. So let's do it fast. So so ZC is root under L by C. So value of L is given 0.9 milliampere. So 0.9 into 10 to the power minus 3, and the capacitance value is 15 into 10 to the power minus 9. 15 nanofarad. So 15 into, so if we do this, you will get the value as 244.94. So this was first one, and determine the phase constant beta, right? So beta is, previously also we have calculated beta, so beta is omega root under LC. So omega is frequency, I guess 50 hertz system, so frequency is 100 pi, so it is 314 point something, right? 100, so 3.142, so let's do here. So, and root under LC is, so you can calculate directly and get the value, which is coming as 1.154 into. So these two are the answers, right? So option B is correct. Any doubt from anyone's? Otherwise, we will move on to the next question. I guess it's clear, right?
Yes, sir, clear.
Okay. So let's move on to the next question. So question 2 is, determine Vs or sending end voltage. So this is the question. So these are the options, okay? I hope the values are with you. We have to find out the value of Vs. So Vr is given. So just calculate. We need to calculate Vs. Load current is given. So IR is given 3 kiloampere lagging than the receiving end. And phase voltage. So these are the values given. So we'll have to calculate the value of Vs. Is it okay? So take some time, and otherwise we'll solve. It will take some time, right? So V receiving phase voltage, we have to calculate the line voltage. So we can just multiply it by root 3. So we can do it later. So for the time being, let's focus on calculating the receiving end phase voltage, right? Let's calculate the sending end phase voltage first. So receiving end phase voltage is given, right? Which is 735 kV. But this 735 kV, this is the receiving end voltage. So when nothing is mentioned, consider this to be a line voltage, okay? So this 735 kV is line voltage. So convert it to phase voltage. So VR phase is 735 by root 3. So VS phase voltage, means sending end phase voltage will be VR phase which is already converted. So cos beta L, just ABCD parameters, right? And the direct voltage, sending end voltage derivation sir has also discussed. I guess you can directly use that equation to find this value. So VR phase cos beta L plus J IR ZC sin beta L, right? This is the VS phase value. So here two things we need to calculate. So ZC already we have calculated, but beta we have already calculated. So beta L we need to just compute. So beta L is 1. Beta already we have 1.154 into minus 3. 1.154 into 10 to the power minus 3, and L is 800 kilometers, right? So 800 kilometers. 800 kilometers. So beta L value will be, so this to 8 into is 1.154 into 0.2. So 0.923 radian, and in degrees it will be into 180 divided by 52.89 degrees. Is it okay? So BL we have calculated. Now directly we can put the values, right? So VS phase, I'm writing PH, right? So it will be smaller notation. VR phase is already given 735 by root 3, angle is 0. This is the reference, and multiplied with cos beta L, so cos of 52.89, and plus J IR. IR is given as 3 kiloampere lagging and 10 degrees lagging, right? So 10 degrees lagging the phase voltage. So 3 into 10 to the power 10 to the power 3, 10 to the power 3 divide by, now angle is also there, so minus 10 degrees you will have to keep, and IR ZC. So ZC we have got 244 in 0.94. ZC is 244.94. Okay, so 244.94, and sin beta L, so sin 52.89. So this is the final value, final equation, and this value that will be coming as this is the final voltage. I have the value of final voltage. Please, anyone, you can divide the final answer by root 3 and get this value, so that won't be ethical. So I'm willing that if somebody voluntarily calculates this one, and we can match.
So 678.96.
Yes, 679. Yes, 679 kV. And but the angle is also there, not only the magnitude. So angle is there, na? J factor is here. J is there.
Yes, let me calculate the angle.
Uh, so some angle will be there. So sending an angle will be in the positive side or negative side. Which one?
Okay, angle is coming 58.2 degrees.
Yes, 58.2. Yes. So VS phase will be on the positive side, right? So from sending, power flows from higher angle to lower angle. This is the basic. And for voltage, so active power flows from, this is a generic understanding. Uh, Convention is that power flows from, active power flows from higher angle to lower angle, and in case of reactive power, from the voltage, it has to be from the voltage difference, higher voltage difference to lower voltage difference, magnitude, sorry. So this is the value. So this is kV. So the line voltage will be, just multiply it with root 3. So we will get the final answer. So final answer is 1176, I guess. 1176.08 kV. I hope it's clear for everyone. So this one is the answer.
So that last part, can you repeat? That reactive power flows from higher magnitude to lower magnitude, or what was that you mentioned? Can you just repeat that once?
Last part.
That part that you mentioned from
No, that
higher.
was, it is just a convention. Means if you do the mathematics part, so you can generally observe. So it's a generic convention that active power flows from the higher phase angle to lower phase angle, and reactive power flows from higher magnitude of, means voltage magnitude from to lower voltage magnitude. It's a generic convention for, but this is based on the mathematical, means based on numericals you can understand. Means here the value is 50. The main aim is to see is that this angle value will be positive or negative. My aim is to just highlight that this will be positive and not negative. Means it can't be negative. So that's the reason I just mentioned. It will be positive 58. Means it's correctly mentioned 58.2. So it will be 58.2 from the sending side to receiving side. From the phasor also you can observe. Generally Vs, this is Vr, and after that some current is flowing. So in that case some lagging current, and when we see that the, means considering this to be higher, this will be like this, let's say. So if it is the resistive drop, this is the reactive drop. So in that case the angle for Vs will be higher from the current side, means the reference value of the current that we consider. So in that case, the Vs will be always more.
Okay, sir.
Yes. So, okay. So let's move on to the next question. So question number 3. Yes. So determine the So this is the question. Determine the sending end current, IS. So options are ampere. So determine the sending end current. So these are the options. So from the ABCD parameters, you can use the ABCD parameter equations. Also, you can take reference. Otherwise, directly current equations are also known. So you can refer it anyway. So when nothing is given, that like previously I have mentioned here, nothing, no specific terminology is mentioned that whether the voltage is line voltage or phase voltage. So in that case, always consider this as a line voltage, this 735 kV. So when you are considering 735 kV as line voltage, that subsequently it is already inferred that the system is in star, right? So if line voltage, we convert it to phase voltage, we divide by root 3. Sorry, yes, divide by root 3. So for the current, then we don't just consider the current here as the phase. Means in the star connection, the phase current is equal to the line current. So current notation will be same. Means the value that we get for the phase current, that will be the same value which is for the line current. Means we don't need to convert that line current and phase current because both are same here, right? So this is the generic convention. If nothing is given, consider that to be a line voltage. Okay, let's solve it. C. Yes, C is the correct answer. Yes, C is the correct answer. Okay, let's do it first. Already we got the answer. So sending end side current is receiving end side current cos BL plus J into I. This is VR by ZC, right? And VR by ZC. This VR is given as line, so in that case, sorry, VR by root 3 to calculate, and whole divide by ZC sine beta. So this is the final form. So already IR is known. IR is 3 kiloampere angle uh, minus 10. Current is lagging, and cos beta L means already we have done 52.82, I guess, 52.89, sorry, 52.89 plus J into VR is already known 735 angle 0 by root 3, and ZC is 244.94, 244.94. So this one is done, and sine 52.89. So this is the final form, and if we calculate directly we will get 2.08, and angle is some angle we will get, right? So 30.9, 30.9. So we just need the final uh, value of kiloampere. So 2.08. So yes. So this is the phase current as well as line current. So you don't need to convert it any way. So this is the final answer. So moving on to the next question. Determine the This is the question. Determine the line voltage at 500 kilometers from the receiving end. Okay. So these are the options. Line voltage. The question is to calculate the line voltage. Okay. This is the type of problem that we have solved previously, but previous case the line kilometer was, I guess, 800, 800, I guess. Yes, 800. So here we need to calculate somewhere between. So 500 kilometer from the receiving end. So if this is the receiving end, VS, VR. So somewhere this is the stretch of the line. So somewhere from the receiving end we need to calculate the voltage here. So let's assume this as a Vx. This is known. We need to calculate here. So obviously the problem that we are dealing with now is similar to the first one, I guess. Yes, this one. This was Vs, so Vs was 800 there, but here it is 500. Please calculate it fast. Anyone solving this, or we'll start solving it together?
So D is the answer.
Yes, yes, D is the correct
Okay.
answer. Thank you. So it's the same problem kind of. We'll have to calculate BL first. So instead of L, it will be X now. So sorry, not BL, beta L. Sorry. So beta X. So let's consider this point X as 500 from the receiving end. So just beta X we need to calculate. Beta already we have calculated 1.154 into 10 to the power minus 3. So here it will be again 1.154 into 10 to the power minus 3 into 500. So this value will be 5769. So this is red. So we convert to degrees, it will be into 180 divided by 33 degrees, 33.05. So we can consider as 33 degrees. 33 degrees. Now once bx is calculated, sorry, beta x is calculated, uh, just use the same formula here, Vs phase. So instead of S, it will become Vx phase. So Vxph, so Vxph is equal to 735 angle 0 by root 3. This is the voltage here, and in cos beta L, so cos beta L, instead of beta L it will be beta x. So beta x we have calculated, so cos 33. So cos 33 plus j IR. IR means the same value, 3 angle minus 10 into 10 IRZC. ZC is 244.92, I guess, 94, 244.94 ZC sine 33. So this will be the phase value. So just multiply the phase value with Vx phase. So as to get Vx line. So you will get the value as 1005.01. So this is the correct answer, D, right? I hope it's clear for everyone.
Yes, sir.
Okay, thank you. So let's proceed to the next question. Same type of question for current. Okay, so determine the line current at 500 kilometers from the receiving end. Same question. Value will be 500. So everything is calculated. Beta x is also calculated. Just use the same previous formula for current and just calculate. We'll match the answers. Mm-hmm. 2.5 ampere since 2.53 ampere d is 3 kilometers. So already we have computed the value of beta x. So same beta x is effective, and just you'll have to use this formula. instead of beta L, it will be beta X again. Right. So let's write the formula here and we will just go through IR IR cos beta L, that will be IR cos beta X. So IR cos beta X plus J, it will be VR phase by ZC and sin beta X. So this is the phase by ZC. So phase means equivalent to line by root 3. So this will give the value of IS. So IR is already known, 3 angle minus 10, and cos beta X means cos 33 plus JVR means 735 angle 0 by root 3, and 1 by ZC means 244.94 and sine 33. So just calculate this. This will be same as the line current, and just need to calculate this. Phase current is equal to the line current in this value. So we'll get the value directly. Anyone with the answer? I hope it's clear. C, yes. C is the correct answer. So answer will be 2.53. So this is the say line current as well, phase current as well as the line current, which is same as its phase. So this is the answer. So I hope it's clear. So we can move to the next question. Yes, any questions?
Sir, in the application, if it is sending end, how can we calculate it?
If it is
Sending end. Can you scroll up one? It is from receiving end point, right? So we took
yes,
500. Then if it is sending end, how to calculate it?
means if we consider this to be from the receiving end side, what will be the sending end?
No, if you are considering from determine the line current, the question is like determine the line current at 500 kilometers from the sending end.
Okay. So in that case also, last means lecture 3, I guess, direct formula sir is derived. So okay, let's complete this. We can discuss one also.
Okay.
Okay. So this is we hope this is a five. Okay, 5-1. Okay, this sixth one we left. So if Vx and Ix denote phase angle, sorry, phase voltage and line current respectively. So this is the question. I hope this question is clear. If Vx and Ix denote phase voltage and line current respectively at x equals to 500 kilometers from the receiving end, then sending end phase voltage is. So we need to uh, find out the best, means the expression of sending end phase voltage. D. Yes, D is the correct answer. So D is the correct answer. So from the sending end side, So when it is 500 kilometer from the receiving end, so that means it's 300 kilometer from the sending end, since the line is 800 kilometers. And for the expression to hold, which would be true in this case, is, so from the x point, means the voltage at x point, if we express the sending end voltage from the point x, let's say this is point x, this is Vr, this is some point at Vx, which is 500 this side, and this is Vx, and this is Vs. So this is 300. So if we express Vs in terms of Vx, so 300 beta, 300 beta, and Ix ZC. So the current at this point will be Ix. So if the current at this point would have been considered, then it would have been IR, but since it is Ix, so if it would have been IR, then the value would have been 800 beta. So there is no such options. For R it is given 500, R it is 300. So these two doesn't hold true. First one is X with 800, so that also don't hold true. But X with 300 with respect to the receiving end, sorry, sending end side, that holds true. So option D is the correct one. I hope it's clear.
Yes, sir.
Yes. So moving on to the next question. Question. So I guess this is the last question of with the same data. Hope. Yes. So if again the same type of question, if Vx and Ix are the phase voltage and line current, same are the phase voltage and line current respectively at x equals to 500 kilometers from the receiving end side, then the sending end line current is Ix cos 500 beta plus j Vx by Zc sin 500 beta kiloampere. V is I R cos 500 beta plus j Vx, sorry, Vr by Zc sin 500 beta. C is Ix cos 300 beta plus j Vx by Zc sin 300 beta, and the IR cos 300 beta plus j into Vr by Zc sin 300 beta. So please choose the answer. Here it's the current C. So let me highlight this. This is the 500 kilometer again. It's the same value. So here we need to say sending and line current. This is the value or equation that is required. So Yes, option C, as you have mentioned, is correct. I hope it's clear for everyone, right? So, so next question is this one. Next question is this one. So you just go through the question till then I'll write the options. So these are the options. Okay. Consider a three-phase 50 Hz lossy power transmission line characterized by distributed parameters per unit length as series resistance this value and series inductance, yes, this value. Shunt conductance is this one and shunt capacitance this one. So the characteristic impedance ZC of the transmission line is, here it is for lossless and lossy, we need to just take care of these two terms. Sometimes these many parameters can also be given and the term lossless will be mentioned. So in those cases, this question becomes a bit tricky. So uh, opt it carefully in the exams also. A. Yes, A is correct answer. A is the correct answer. So, so for lossy transmission line, we have directly the equation ZC is equal to root under L by C, but here it is lossless. So calculation, it's a hectic one, nothing else. So the value of ZC will be given by Z by Y, right? So Z means R plus J omega L and Y means G plus J omega C. So we'll have to just fit in these values, uh, 132 plus J omega is 50 hertz given, so 314.2 and L is given. L is 0.88 into 10 to the power minus 3. So this one, the numerator part, and the denominator will be G. G is 20. So 20 into 10 to the power minus 6 micro Siemens is given. and shunt is J into 314.2 into 13 nanofarad, so 13 10 to the power minus 9. So it's just calculation intensive, nothing else. So value answer will be 122.51 angle 26.47. So this is the value of characteristic impedance. Okay. So moving on to similar question based on these values. The question is same. No, sorry. The parameter values are same. The phase constant beta of the transmission line corresponding to the parameters given in the previous question. So the phase constant beta we need to calculate of the transmission line corresponding to the parameters given in the previous question. So I'll just write the options. Those per sorry, net per is 3.38 into 10 to the power 6 net per kilometer, and 3 is 0.06 into 2 net per kilometer, and D is 1.5. So this is the question. Parameter values are this one, these one. So this is the question. I think the question and the parameter values are visible in a single screen. So the question is lossy. So just keep in mind the factor lossy transmission line. So the difference between, I hope the values you have noted down so that I can scroll my screen. Right?
Yes, sir.
So, so in the lossless transmission line, so you can directly, we can directly use the value beta L, J beta L for denoting this uh, gamma, but here since this is for lossless, but for lossy line gamma is alpha plus J beta. So sorry. So here beta we need to calculate as, so beta is root under, so we know that gamma is root under yz, yz. So then beta will be just the imaginary part of, or may say gamma. So this we need to calculate just for lossy. So this is the question. So let's solve it. So beta is equal to imaginary part of yz, and root under yz means root under y means r plus, sorry, root under yz of z means r plus j omega l, and g plus j omega c. So this is the ultimate. So, so we have the values, just fit in the values. R means 0.132, 0.132 plus j omega l, omega means 314.2 into L is given 0.88 into 10 to the minus 6. And so this is this square root, and on the other one g means 26 plus j into 30 plus j into 314.2 into 13 into 10 to the minus 9. So this is inside other square root. So if we just take these two things into consideration, the imaginary part would be, so anyone with the answer, or we'll just, I hope it's clear. This is a simple problem. We can directly write the answer. I can directly write, yes, no, C, no, C is not the correct answer. I hope there is a just a simple calculation mistake, because the option, the answer is D here, okay. So we are running short of time, so we have to finish these two. So answer is D. So answer is, so for the imaginary part it's 1.54 into 10 to the power minus 3 rad per kilometer. So this is the final answer. Okay, I hope it's clear so that we may move on to the next question. So question, this is for a symmetrical. So the question is for symmetrical and reciprocal power transmission line with line parameters A, B, C, D. If A is equal to this value, B is this value, then calculate C. D. So for symmetrical and reciprocal power system, what's the condition?
AD minus BC equals to 1.
D minus DC equals to 1. And
A equals to D.
yes. So these two are the conditions. So A equals to D means D value and A value are same. So this will be 603. So just plug in these values to calculate C. So C will be AD minus 1 by B. And all the values are given. So 6.603 whole square minus 1. Um, ah, yes. I hope it's correct. I guess B is J 195.33. So the answer will be option D is the correct answer. So answer will be J 0.0032. I hope it's clear. So So, so another question here. So I'm writing in notation form. So VR you can understand that it is the receiving end voltage, right? So
Yes, sir.
here it is receiving end voltage. So here is given 220 kV, and this is and load connected is at the receiving end is 100 megawatt. Power factor is 0.9 lakh, and is given as point. I hope this is the kind of same question. So in the form of okay, just PO point 0.98 angle 2 degree, and B is given as 110. So calculate VS. Calculate VS. This is the question. So receiving end power, PR is the receiving end power, 100 megawatt. Okay, let's solve it together. So, so when receiving end power is given PR 100 megawatt, so can we calculate the reactive power given the power factor values? Any ideas?
Sir, 48.4 megawatt
Yes.
as
Yes.
VR.
So this will be 10 of cos inverse 0.9 and multiplied with 100. So this will become 48.4 MVA. So once we have these two values, PR and QR. So we can find out the current, right? Since voltage is given, receiving and voltage is given, and consider this as a reference voltage as well as the phase voltage. So this is the line voltage, so convert it to phase voltage, because phase current we need to calculate. So once we have everything in phase, then we can convert to line, right? So just IR phase. So what will be the receiving and current in phase? So it will be 100 megawatt means, so S, this what will be S? Can represent it in P plus JQ. We can represent it in this fashion, and divide by voltage VR. But this VR is in phase, sorry, line. So it's 100 plus, and everything is in megawatt. So this is the three-phase power. So considering this to be three-phase power, so we need to divide by 3. This is the total power. So considering per phase, so power gets divided by 3 in three-phase line balanced system. So power is 3 times, right? So, and VR is 220 by root 3. So okay, another thing is this is in megawatt and MVA. So MVAR. So this is MVAR. So this is, and the value here is 10 to the power 3. So kV is 3. This is 6. So then entire thing is divided by 3. So to calculate this value, we will get some value. So we will have to calculate, and I hope you are getting this correctly. So this value will get, this is the phase current, okay. So sending and voltage is just VS is A, VS, and A and B values are given. So A VR plus B IR. Thus this one you will have to, IR phase you are getting, VR phase you already know, so VS phase you will get. So accordingly, are you calculating? So you, I can wait. So A and B values is 0.98 angle 2. VR is already known, 220 by root 3, and B is 110 of the TS and the current. IR phase, anyone calculated the IR phase? So this IR phase, you just plug in this IR phase here. So this value will be the same value, and you will get the value of VS line. VS line sending end. So you just calculate and get the values. In the meantime, somebody asked this. So you have, if somebody asked, I guess, regarding the
Sending in voltage, if we calculate from the sending in
yes,
voltage.
yes, yes. So if you see in the lecture, I guess. So considering these same numericals can be solved from the sending end side. So if the value suppose you are given from the receiving end, okay. So in that case, or any point which is h distant away from, so you have the direct equations, the like the sending end side means in the same manner. Here it will be Vs and Is means the on the right hand side, and in this case also, so it will be Vs cos gamma x plus uh, minus ZCIS sin gamma x, and in case of Ix also it will be 1 by ZC minus JVS sin beta x. So one thing is that if it is lossless or lossy line, so in the notes also you will get to see if I have the notes here. So considering at a lossy line, so to consider this to be more generic case. So in that case, plus ZC IS sin gamma x. So this is the value if we see it from the means these are the equations if we see it from the uh, receiving end side, sorry, sending end side. So if some numerical is given where Vs is given, and this x value, if it is this is, let's suppose, Vs, this is Vr, and somewhere it is Vx. So if Vx is x distance, and if it is in any numerical, if this value is 800 kilometer, okay, and if this value is 500 kilometers, so you can easily calculate. If it is, this will be 300 kilometer, so you can easily calculate this gamma value for lossless line. It will be directly beta x. For lossless line it will be beta x. So the influence of gamma will vanish, right? So it will be beta x, this will also be beta x. So if it is receiving end, so Vx will be the subscript x will be replaced with the R values, means Vr, and in the x value will be the total distance between Vs and Vr. I hope it's clear now. Yes, yes. So same numerical values. It's just if you go through the notes, in the portal you will get the entire week's lecture notes, I guess. So there you can see once same type of numericals may come from the receiving end side. We have discussed from the sending end side can be the value. So these two equations needs to be just followed. So all things are same. So characteristic impedance, these current Vs, gamma x. So gamma x will become beta x if the system is lossless. So otherwise gamma x will be gamma x. So is it clear? Okay. Okay, then these values I guess you can calculate this value. This answer I also don't have. This is the numerical, the answer. So you can calculate and we can discuss on the next upcoming week. So you can we'll verify it once. Otherwise you can calculate. This is the final value. So this is the phase value. So for the line current line voltage, so you'll just have to multiply with root 3. Root 3 into Vs phase. So that will give the Vs line. This will be the final answer. I hope it's clear. Okay. So that's it from my side today. So if you have any queries, you may ask, or we can end today's session. My aim with the numericals that I have targeted, so it's complete. So thank you for your active participation.
Thank you, sir.
Thank you. Thank you. Okay. So we'll meet on next Tuesday. Thank you. Good night.
Sure, good night.